Hi everybody. Today we're going to talk about pressure distributions or forces on submerged surfaces. So we'll review hydrostatic forces on submerged surfaces, both horizontal and vertical forces on a flat plate, and then forces on a curved plate. So here's the basic picture. Here's this diagram you might recall. Here's the plate submerged under a liquid surface, and if I look at it on edge, this is what I see, and when I flip it to its side and look at the plan view, this red shape here is what I see. The nomenclature is that the CG is, again, this cool BMW looking symbol, denotes the center of gravity of the plate itself. However, the CP acts below that at all times, right? Because pressure increases with depth, it pulls the CG lower than the CG for any submerged surface. The CG is located by looking at the mass moment of inertia of the particular plate, and then the distance to the CG is this HCG from the free surface. The CP is a little harder to find. We actually have to do a moment balance and integrate over the plate. We can find the force acting on the plate, the resultant hydrostatic force, by integrating the pressure over the plate. That's how we would do it from first principles. But often we just jump right to the integrated form, assuming constant density and constant gravity in the fluid. This integral, like if this is constant and G is constant, then those two terms pull on out of the integral, and you're just integrating the height with respect to dy dz or dx dy. That's just the area of the plate. And so you end up with the simple relationship that the force is equal to the hydrostatic pressure plus the atmospheric pressure, so that's rho gh, plus the atmospheric pressure times the area. That'll give you a force. And it's located at ycp, which is the distance below the CG of the x-axis moment of inertia times sine theta, the angle of the plate, divided by hcg times A. And here's XCP. Now the thing that I don't want you to forget is that HCG, which appears here and appears here, is the distance, the straight line distance from the free surface to the CG, not the CP. To get to the CP, we go down a depth, YCP, and over a distance, XCP. Now for curved surfaces, what we're going to do is break those surfaces into two components, right? So if we have a curved surface, like this is a plate that extends into the page, and the top of the plate is a distance h naught from the free surface, we would know that just on the top you have an increasing pressure with depth. Pressure always acts normal to the plate, so each vector is curved to be normal to the plate. And we can break this plate into two components, the vertical plate and the horizontal curved surface. So we can think about the vertical plate as the projection of our curved surface onto a vertical surface, which would have a pressure distribution, and then we can use the previous equation to calculate that. And then the vertical forces are just the weight of the water above the plate. So we can replace these kind of distributions of forces with resultant forces. So the resultant force acting on the curved plate is made up of two components, the horizontal and vertical components. And it's just as I've drawn it here, it's not necessarily true that this horizontal reaction force, that the total reaction force acting on the curved surface touches the curved surface. It must be normal, but the resultant force could be floating up off the plate. We find it by first locating the horizontal force, which for a flat plate is rho gh times A. And it's located a distance, a vertical straight line distance down yc sub p. And remember, when you do this projection, this A is the projected area, not the original area of the plate. This this horizontal force can just be translated over, and that would be the location of the horizontal force, which fixes the location of the resultant vector. The vertical forces are simply the weight of the plate, so you would calculate the weight of each one of those volumes, or you could break it up into as many volumes as you need. So that's why it appears as the sum of the density times volume, which is mass times gravity. So it's just the force. Each of the vertical forces acts at the location of the CG for each of the components that you have. And again, the location through the CGs, the equivalent moment would then determine where that location of forces is. All right, so let's do a quick example. Imagine you've got this curved surface. It's being resisted by this externally applied pressure force P. It's hinged at this location C. And so the gate would naturally, if it's got water on top, it would want to open. So this P force is holding it in position. So a quarter circle gate CB extends into the page and is hinged at C. Find the horizontal force P required to hold the gate stationary. The width into the board is B, which is 3 meters. Neglect the weight of the gate. All right, so we could start this by breaking it up into its components. The first one being the horizontal force. So the horizontal force is here, somewhere acting at the CP, some distance YCP below the CG, and the distance HCG is this guy right here. Do you know what that is? Right, it'd be 3 meters, right? So I can calculate this force by just using rho GHCG times A, and I get 176. If you think that is the reaction force P, you could find what you think might be the answer, but of course you would be wrong. You're neglecting the forces that are acting at, the reaction forces acting at C. There could be some reaction forces acting at C. So in order to actually calculate what P is, we need to, if we still don't know what the forces at C are, we could perform a moment balance about C, and then that would relieve us from having to know what those reaction forces at C are. But we're going to need to know the vertical forces to do that. Now, to finish up with the horizontal force, we know that we can calculate the YCP, which is that little distance there below the center of gravity, so that we can perform the moment balance. And if I just chug through the math here, I get 1/9 meters. All right, the vertical force is just these two areas, or volumes, I should say, the weight of those two volumes. So it's the density of water times volume 1 and the density of the water times volume 2. Easy enough to figure out. This is a square cylinder into the board, and this is a quarter circle cylinder into the board. So they have easy enough geometries to calculate. This is the square times 3 meters into the board, and then a quarter of a circle times 3 meters into the board. And I calculate these two resulting forces. And then I need to know what their positions are. So for this symmetric shape, it's just 1 meter over if it's 2 meters across the top. And then for this guy right here, you may recall that the center of gravity is 4r divided by 3 pi. So this is my free body diagram of what it looks like. Easy enough to sum the moments of this free body diagram. P times this, that should be 1 meter. P times 1 meter. The horizontal force is just the total distance down. It's the distance left over when I go the total 4 meters minus the HCG minus YCP, and then these forces times their respective moments to get me the moment arm to C, and I end up with P of 352,000, and that looks like maybe this guy right here. All right, I hope you enjoyed that. Maybe you remembered some of your hydrostatics, and I'll see you again next time.